Great. And then I start to share my screen. Great. Then let's keep going. Okay, so in the last class, we started to see WRB soil classification according to the reference soil groups. And then we saw some soil profiles that has some restrictions to root growing, to water percolation. And then now we start with the planosols, okay? The planosols are those soils that, first of all, they cannot be classified as the previous reference soil groups. So we always need to be sure about that, okay? So when you try to classify a soil according to WRB, you must start in from the beginning, from the histosols and then the cryosols, and then following the order until find something that fits for all the classification, okay? So the planosols are those soils that they cannot be classified as the previous reference soil groups, and they have an abrupt textural difference in the first 75 centimeters from the mineral soil surface, and having with the range of 5 centimeters directly above or below the abrupt textural difference. So they must register an increase, a huge increase of clay content between two horizons, okay? And this increase of clay content should be between two horizons that are connected. So we have, for example, in this photo, we have an A horizon, an E horizon, and then the B horizon. And this network horizon below could register a huge increase of, sorry, a huge increase of clay content, and or I can just register an RGX horizon with a huge clay content, and this huge clay content, it's much higher than the overlying horizon, and because of this, we we register the abrupt textural difference. Okay, this should be in the first 75 centimeters below the soil surface, and this huge difference of clay content should be in a range, in a distance of 7 centimeters or below or less than this. So we must register a huge difference of clay content up to 5 centimeters. So for example, I will consider the top of this RGX horizon, and I will count 5 centimeters above. So in this case, in this photo, 5 centimeters above this RGX horizon is this E horizon. So I must compare the clay content, the texture of this E horizon and this B horizon, okay? I cannot compare the clay content of this RGX horizon with this A horizon, okay? Because it's much more than just 5 centimeters. So in the case of the planosols, this huge increase of clay content, it must be in a very few distance, in a very small distance. So just few centimeters, like 5 centimeters or even below of this, I must register a huge increase of clay content. So this huge increase of clay content will reduce or limit the root growing, okay, through the soil profile. And I also must register stagnic properties, in which the area of reductomorphic features plus the area of oxymorphic features, it's equal or higher than half of this volume, okay? So I must register this kind of colors, like reddish colors or grayish colors, okay? I can register both. These stagnant properties, they came from the low permeability of this argic horizon. So because the water cannot easily penetrate through the soil, so we can start some reduction. So we have some reductive features or reductimorphic features or oxymorphic features because of the changing between oxic and anoxic conditions. So we can see in some cases some gray colors and in some cases some yellowish or reddish colors. So in this photo, you can see very easily this reddish colors showing that we have stagnant properties, but in this case we have more oxymorphic features. I'm sorry, oxymorphic features. So if you reduce both, okay. If you just reduce one, also okay, but at least half of the volume of the horizon should register reductimorphic or oxymorphic features. And reducing conditions for some time during the year in some parts of the soil volume that has the reductomorphic features. So I must register reducing conditions. How can I see these reducing conditions? We have some indicators like chemical indicators like alpha dipyridyl, that it's a kind of chemical reaction with the soil. You just need to drop some of these indicators in the soil, and it will indicate the presence of iron 2, free iron 2, indicating that we have reducing conditions. Okay, so it's just a kind of chemical reacting that you just drop on the soil, and you can see it has a transparent color, so you cannot see the color of this alpha dipyridyl, but when it has contact, when it gets contact with iron 2 especially, it has a very strong reddish color, like really strong, like blood. Okay, so you can easily indicate that you have reducing conditions in that area because you have free iron 2 or just have iron 2 because of these reducing conditions. Okay, so the planosols are those soils that has some restrictions to root growing, to water percolation because of huge increase of clay content in a very small distance between two horizons. Okay, and because of this, you register some oxymorphic or reductimorphic features. We have also the stagnosols. The stagnosols are those soils that register stagnant properties and cannot be classified as the previous options. Okay, so this photo is a very typical stagnosol. You can see, you can see here that the stagnosols are those soils that, of course, they cannot be classified in the previous soil orders, in the reference soil groups, but then they have stagnant properties. And we already know what are stagnant properties. Stagnant properties are those properties that are expressing the limited water percolation through a horizon. Okay, so we have, for example, a heavy rain, and this heavy rain induced some water percolation through the A horizon and also the B horizon. But when the when the water achieves the B horizon, the water can has some limitations or some reducing of the velocity because, I don't know, maybe the B horizon has a higher clay content, or the B horizon suffered some eluviation of clay, and because of this we have lower macroporosity, or because of this we have less water conductivity through the B horizon, and then we'll have some stagnation of water. So the stagnosols came from stagnation of water. So these stagnant properties, they start to express as a reducing in the voids. So the voids between aggregates, they start to represent, and say, some gray colors. So you can see these gray colors expressing reducing of the walls of the aggregates. So the walls of the aggregates start to reduce iron.
أشهد أن لا إله إلا الله، أشهد
Um,
أن محمدا رسول الله. حي على
sorry, I
الصلاة،
think that
حي على
someone.
الفلاح، إقامة الصلاة، إقامة الصلاة. الله أكبر، الله.
Okay, guys. I will mute you all. Okay, so if you have some question, you just open your microphone. Okay, it will be much easier. So let's return. Great. So as I said, the stagnosols, they register the stagnic properties, and that are those grayish colors that we can see in the voids or between the aggregates, okay? You can easily see here and all of this horizon, they are these technical properties, expressing, reducing of the walls of the aggregates because water is stagnant in these voids. So we have dominance of oxic conditions, especially inside the aggregates. But the voids will have reducing conditions because the voids are fulfilled by water, okay? And this a huge amount of water in the voids induce some reducing and then reducing conditions with reductimorphic features in the aggregates. So the stagnic properties in which the area of reductimorphic features plus the area of oxymorphic features is equal or higher than 130 of the area of the mineral soil surface to a depth of 60 centimeters or to a continuous rock, whichever is shallower. So we can see that the stagnic properties starts around here and are much more common and abundant here, but they start around 50, 60 centimeters. You can see here, especially these grayish colors, okay? And reducing conditions for some time during the year in some parts of the soil volume that has the reductimorphic features in the first 60 centimeters from the mineral soil surface or to a continuous rock, whichever is shallower. So again, these reducing conditions we can see very, very easily using alpha dipyridine, a chemical that can react with the iron 2 in the soils and show that we have some reducing conditions, okay? Oh, another photo that you can see very easily, this grayish color between the aggregates showing that water cannot easily percolate through the soil. And also these photos I already showed you, you can see that only in the voids we have this grayish colors, okay? And here the same. Always when we have some root growing or some cracks showing the voids, these voids, they have these grayish colors, and inside the aggregates, they are yellowish or reddish, okay, because they have oxic features or oxic conditions are dominant conditions. Here is the same. You can see that the pads, the aggregates, they have dominance of reddish colors, but inside the cracks or inside the voids, they have this reductimorphic features. They have these grayish colors. And now we start to see some soils that they don't have any problem to root percolation or water percolation, but they can concentrate iron or they can concentrate anything in the soil. And let's start with the needy soils. The needy soils are soils that cannot be classified in the previous reference soil groups. And first of all, they have a niddic horizon, and the niddic horizon we saw, they are connected to those horizons that has a lot of shiny surfaces. So these shiny surfaces, they shine a lot, so we can see some clay orientation on the aggregates because of the shrinking and swelling. These niddic horizons, they commonly register a huge content of clay, and this huge content of clay, it's not connected to any clay alluviation, but basically because they are formed by weathering of mafic materials. So it's quite common that the Nedic horizons came from weathering of basalts. So because of the easy weathering and destruction of basalts, you produce a Nedic horizon, a horizon with a huge content of clay that can suffer some shrinking and swelling, and this shrinking and swelling can orientate the clays on the pads, walls, and these could create this shiny faces, okay, these shiny surfaces. This Nedic horizon should be registered in the first 1 meter below the soil surface. On the photos, using the photos is quite hard to identify the native soils. So yes, it seems like a Ferrol sol, a typical Ferrol sol for us, but when you get closer, when you describe the horizons and the pads, you can see very, very easily the shiny faces. And also, it's quite common that you register a strong structure. So it's quite common to see sub-angular blocky structure or angular blocky structure, some prismatic structures too, but all of them, majority of them are moderate to strong structures, showing that we have a strong grade of these horizons, okay? And much more important than the native horizon, we need to find from the mineral soil surface to the native horizon a clay content that it's at least half of the weighted average clay content of the native horizon. This is showing you that you don't does not register a huge difference of clay content between the horizons. So the E horizon or the A horizon shouldn't register a huge difference of clay content with the Nedic horizon, with this B horizon. Okay, so the clay content in all soil profiles should register a similar clay content and no vertex horizon starting above or at upper limit of the Nedic horizon. Why we are excluding the possibility of the vertex horizon here? Because we are talking about a horizon that has a lot of clay content that suffers shrinking and swelling, and because of this you produce some clay coatings, you produce some clay surfaces, some shiny surfaces. And we are excluding the vertical horizon because this soil cannot register slickened sides or wedge-shaped structures. So the morphology of the niddy soils are not connected to the vertisols, are quite different, okay? So let's think about the horizon and a soil that register shiny surfaces, but no wedge-shaped aggregates, no slickened sides, definitely not huge cracks. So it's not a soil that has huge cracks, as you can see, okay? So the shiny surfaces you can easily see here. So for example, this area has no shiny surfaces, but these areas you can easily see how this material can shine. And this could be connected to the shrinking and swelling that produce some clay orientation on the surface. Okay. And we also have the ferrule soils. The ferrule soils are the most typical soils in the tropics, especially in the wet tropics. Okay, so they are those soils that cannot be classified in the previous reference soil groups. And first of all, they have a ferralic horizon in the first 150 centimeters below the soil surface, and they cannot register, oh, I'm sorry, and no RJEC, or they cannot register an RJEC horizon starting above or at the upper limit of the ferralic horizon. So I cannot register above the ferralic horizon, an RJEC horizon, a horizon that register some clay skins, some shiny surfaces, or a higher clay content of clay than the E horizon or the A horizon, okay? And below this, oh, no RJ horizon starting above or at the upper limit of the ferralic horizon. And I'm sorry, unless the Arctic horizon has. So if we register this Arctic horizon above a Ferhalic horizon, so in this case, this Arctic horizon should register in this upper 30 centimeters or from whichever is shallower, one or more of the following characteristics. First of all, less than 10% of water dispersible clay. So I should register a low content of water dispersible clay, showing that register a strong structure, okay, strong grade. Or delta pH, that's pH potassium chloride less than pH in water, equal or higher than zero or positive values, both in one-to-one solution. So this positive delta pH or delta pH that is equal to zero indicates a very strong wafering and leaching. So this very strong wafering and leaching is indicating that now we have a huge concentration of iron oxides, especially as goethite and hematite. So this very strong chemical wafering now produced something that's quite wafered. That's what we usually identify as a Ferhalic horizon. Okay, or the other option is that this Arctic horizon register 1.4% of soil organic matter or organic carbon, 1.4% of soil organic carbon or more than this. So we must register a high content of organic carbon in this Arctic horizon. Okay, so at least one of these three properties of these three characteristics must be identified in this Arctic horizon if we register an Arctic horizon above the Ferhalic horizon. But of course, in both cases, we must register a Ferhalic horizon with or without an Arctic horizon. We must identify a horizon that concentrates iron oxides and aluminum oxides because an intense chemical wafering and leaching. Okay. Now let's see horizons, or let's see soil profiles, reference soil groups that register a high content of organic carbon. These soils can start to be classified as Chernozems. The Chernozems are the first reference soil groups that were studied by Dokuchaev in the past, and these soils, they register a thick organic material, organic and dark horizon at the surface. Okay, not organic, I'm sorry, because you must remember that organic layers or organic horizons, they must register at least 20% of organic carbon. But what I want to say is that the organic carbon content in the surface horizon is quite high. Why? Because to identify a Chernozem, first of all, we cannot classify the soil profile in the previous reference soil groups, and the first of all register a Chernak horizon. And the Chernak horizon, you should remember, that are those horizons that register a very dark, a very strong dark color. We must register some strong or moderate grade. We should register some high organic carbon content. Of course, not high as 20%, but quite high, like 1.6, 1.8% of organic carbon. A dark color, a strong grade, a high content of organic carbon, and a high thickness, okay? And also some secondary calcium carbonate concentrations. So we must register all these characteristics in the Chernak horizon. And also, besides this Chernak horizon, we need to register starting at 50 centimeters or less than this. We need to find the limit of the Molech horizon, and if present, above a petrocalcic horizon, a layer with petrocalcic properties with a 5 centimeters or more of thickness, or a calcic horizon. So, for example, here you can see starting around 20, 30, 40, or even 50 centimeters. This horizon, that's the petrocalcic horizon. Okay, the petrocalcic horizon is a horizon that was cemented by calcium carbonate. So we have in this case a churnic horizon above a petrocalcic horizon. So it because of this, we can register that we have a chernozem because also have a base saturation that's equal or higher than 50% from the mineral soil surface to the layer with petrocalcic properties or the calcic horizon through. Okay, so we must register below this churnic horizon a high base saturation. Okay, so we can easily identify that we have a high base saturation in this photo because we have cementation by calcium carbonate. So because of the cementation by calcium carbonate, we know that we have a plenty of calcium and maybe also a huge amount of magnesium. Both of them are counted for bases. So both of them count for base saturation. So we know that the base saturation should be high in this soil profile. But of course, we can run some chemical analysis to certify this, to be sure that we have a huge amount or at least 50% of base saturation in this soil profile. Okay, if we does not register the petrocalcic horizon, we must register something with petrocalcic properties. That's a weak cementation or a calcic horizon, a horizon that shows you some white spots, some white dots in the soil profile, showing that you have some secondary calcium carbonate precipitation. Okay, this is the case of the calcic horizon. Oh, sorry. These photos, you can see very easily the cementation of the soil by calcium carbonate. So you can see very easily the petrocalcic horizon, okay, below the churnic horizon. The churnic horizon, it's above, it's this darkish and thick horizon, okay? Another photo, you can easily see this photo with this material, with calcic, a calcic horizon, because you have some precipitation of secondary calcium carbonate, especially here, you can easily see here. And this horizon, this darkish horizon, a churnic horizon, a thick horizon with dark colors and strong grade, high base saturation, and a high organic carbon content. If a soil cannot be classified as a chernozem, maybe it could be classified as a castanozem. A castanozem is a soil with a molic horizon. Okay, so in this case, you must remember the molic horizon, it is less oxygen than the molic horizon, than the churnic horizon. So it also demands high thickness. It also demands darkish colors. It also demands a high base saturation. It also demands a high organic carbon content, but the organic carbon content could be lower than the churnic. The thickness could be lower than the churnic, and the color could be less darker than the churnic horizon. So this horizon, it's a molic horizon. Okay, it's dark, yes, but not too dark as the other one, and also has a high base saturation and strong grade, and it's not thick as the other. Okay, so it should register a molic horizon, and starting at 70 centimeters or less than this, below the mineral soil surface, we have a petrocalcic horizon, a layer with protocalcic properties, with at least 5 centimeters of thickness, or a calcic horizon. So in this case, we have here in this case a calcic horizon. Okay, we can see this white spots, these white dots that shows us secondary calcium carbonate precipitation. So we have below the molic horizon, we have this calcic horizon, and the base saturation should be equal or higher than 50%. Okay, with this in this protocalcic properties or the calcic horizon. So here in this case, because of the huge amount of white spots, I can easily tell you the base saturation will be higher than 50%. But if you want to be sure, just take some samples, run some lab analysis, and we will be sure about the base saturation, okay? So a soil that cannot be classified as previous, especially the Chernozans, with a molic horizon above a calcic horizon, a petrocalcic horizon, or a horizon with protocalcic properties. Okay, so here we can see, for example, these roots with some calcium carbonate precipitation. Here we can see some calcium carbonate nodules, okay, showing that we have secondary precipitation of calcium carbonate. And here I already also showed you this photo, these white spots with calcium carbonate. We can just drop some acid and indicate by the bubbles, by the reaction, that we have some calcium carbonate precipitation. And the last option, actually the one of the last options, considering soils with a huge amount of organic carbon, but mineral soils, we have the felsens. The felsens are those soils that cannot be classified in the previous reference soil groups and register a molic horizon. So again, here we have in the first 20 centimeters the molic horizon with darkish colors, with strong grade, with high base saturation and a high organic carbon content, but it's not a Chernec horizon, okay? And a base saturation that should be equal or higher than 50% below the molic horizon, and up to the first 100 centimeters, or a limiting layer. For example, there are layer like here. Okay, so we can register here below this molic horizon a high base saturation. So these we have a CR horizon that shows some obliteration of the rock, but we can see, let's say, some pieces of rock. So, okay, we can ignore this section. And here in this section is the BI horizon. The base saturation should be equal or higher than 50%. So in this case, I have a molic horizon above a horizon with a base saturation that's equal or higher than 50%. These are the felsens, soils with high base saturation and a molic horizon. Okay? So you can see all these photos, and all of them are felsens, soils with darkish colors, but they cannot be classified as Chernec horizons. And below this molic horizon, I cannot see any calcic horizon, I cannot see any protocalcic properties, and I cannot see any petrocalcic horizon. So no cementation by calcium carbonate, no secondary cementation, no secondary precipitation of calcium carbonate. And these horizons are below a molic horizon. So the easiest difference between the Chernozans, Castanozans, and felsens. The felsens, they does not register any cementation by calcium carbonate, and they does not register any secondary precipitation of calcium carbonate. So these are the felsens, soils with darkish colors at the surface, high content of organic carbon, high base saturation, and a strong grade, but no secondary precipitation of calcium carbonate, no cementation by calcium carbonate. The difference between the castanozans and the chernozans are what we can find at the surface. In the chernozans, we find the Chernec horizon. In this castanozans, we find the molic horizon. So the difference are how thick is the mineral soil surface, how dark is the mineral soil surface, how enriched in organic carbon is the surface, and how strong is this surface, okay? Is this mineral soil surface. So the thickest, the darkest, and the richest organic carbon above petrocalcic, protocalcic, or calcic horizons. Here, less dark, less thick, less strong, above petrocalcic, protocalcic, or calcic horizon. And here, less dark, less enriched in organic carbon, less strong or more weak, above nothing, above no cementation of calcium carbonate, above no precipitation of secondary calcium carbonate, but high base saturation. The base saturation should be high, equal or higher than 50%. Okay? And then we met the less organic enriched soil, but a mineral soil. These are the umber soils. The umber soils are those soils that cannot be classified in the previous soil that we saw, the reference soil groups, and they must register an umbric horizon or a molic horizon or an arctic horizon. Okay, so the umbric horizon, we already know it's this one. The umbric horizon are those horizons, those surface horizons that register a darkish color, and they are enriched in organic carbon. They register a strong grade. They are thick, but the base saturation is below 50%. This is the only difference between Molic and umbric horizons. Those that are classified as Molic horizons, the base saturation should be equal or higher than 50%, and the umbric should be below 50%. Okay, so basically the difference is the base saturation. And the Arctic horizon, we already know, are those horizons that are anthropic format. They are formed by humans. So humans can add, especially organic materials at the surface, and they can mix with the soil and produce a surface horizon that it's enriched in organic carbon and has darkish colors, and they have strong grades, and they are thick. So if I register a soil with an umbric horizon above something with high or low base saturations, I should classify as an umbrasol. If I found something with a molic horizon, so a surface horizon that has high base saturation above some horizons with low base saturation, I cannot classify as a philzen. I should classify as an umbrasol. Okay, so a horizon with a high base saturation above something with a low base saturation, umbrasol. Or the last option, if I found something as a Arctic horizon above something with low or high base saturation, no problem. Both will be classified as umbrasols. So an Arctic horizon above low or high base saturation, in both cases, umbrasols. Okay, so the only option here of low base saturations is the for the molic. So if I find a molic, definitely below the molic horizon, I must identify a horizon with low base saturation. In the other cases, umbric and Arctic, both cases can register low and high base saturations below the surface horizon. Okay, so all of them are umbrasols. Something that's quite interesting to mention is that a lot of histosols, soils that are classified as histosols according to soil taxonomy, they are classified as umbrasols according to WRB. Why? Because the content, the minimum content to identify organic layer in the WRB and soil taxonomy, they are different. Remember, in the case of soil taxonomy, it's just 12%, in some cases, 8%. In the case of WRB, the minimum content must be 20%. So to identify organic layer in the WRB, I must identify at least 20% of organic carbon. So to classify a soil as a histosol in the WRB, the minimum content is 20%. But as I said, in the soil taxonomy, it's just 12%, in some cases, 8%. So a lot of histosols, soils that are classified as histosols according to soil taxonomy, they are classified not only not as histosols in the WRB, but as umbrisols in soil in WRB because of the higher organic carbon content threshold for WRB. Okay, now let's see some soils that has some concentration of materials that also can express some root limitations, root growing limitations, okay? The durisols. The durisols are soils that are not classified or cannot be classified in the previous reference soil groups, and they have a petroduric or duric horizon starting in the first 100 centimeters below the soil surface. So the petroduric and duric horizons are those horizons that express some precipitation of secondary silica, as you can see in these layers here and here and here. But the difference between them is that the petroduric horizon is that horizon that have a strong cementation by this secondary silica. So the horizon cannot be easily destroyed or broken by my hands or by a knife because the concentration of secondary silica was too big that fill out all the voids, all the pores, and then cemented that specific section of the soil. And then I register a layer, a horizon that was cemented by secondary silica. Okay, so if I cannot classify in the previous reference soil groups and I register a petroduric or duric horizon in the first 1 meter, yes, this soil should be classified as a durisol. Of course, as I said, it's quite common to find these soils in arid and semi-arid regions because they are much more common in dry lands, in areas that have a high pH close to the surface, and this high pH was induced by precipitation of salts, and because of this high pH, we have some dissolution of some silicate minerals and migration of silicon until you find an acid or less alkaline horizon that induce the precipitation of this secondary silica, and the secondary silica can fill out totally the voids and the voids or pores of a horizon and create the petroduric or just fill out some of these voids and form a duric horizon. Okay. We also have some soils that are expressing secondary precipitation or precipitation of something. And in this case are the gypsols. The gypsy sols, they are not classified in the previous reference soil groups, and then they register a gypsic or petrogypsic horizons in the first 1 meter. And so first of all, let's remember what is the gypsic or petrogypsic horizons. The gypsic horizon is those horizons that express gypsum precipitation. So we have some secondary gypsum precipitation with this whitish colors too. Okay, so the gypsum, if you cannot remember, it's calcium sulfate. This calcium sulfate is a very unstable mineral that only can precipitate at very dry regions, like the driest semi-arid and arid regions that you can think. And in this dry, very dry regions, you can precipitate some calcium sulfate, and also sometimes this precipitation could be quite strong, and we have some cementation of some layers or horizon because of this precipitation. Okay, and we cannot register no argic horizon starting above or at the upper limit of the gypsic or petrogypsic horizon unless the argic horizon contains secondary gypsum or secondary carbonates throughout. Okay, so I cannot find an argec horizon above the gypsic or petrogypsic horizon unless this argec horizon it's also something that precipitates gypsum or even secondary carbonates. Okay. Oh, a good question about how to identify gypsum at the surface. We cannot do that. We cannot do that very easily. Okay. We have some description of the morphology of the crystals, but this only works when the crystals are quite big, like for example, at sand size or even higher than this. But for example, in this photo, we does not have sand size crystals of gypsum. So the only way to identify if we register or not gypsum is again dropped acid. Okay, if we have this whitish colors and you drop acid and you register no reaction, so no reaction, I've dropped some acid. So okay, in this case, I can be more sure about gypsum precipitation. But if reacts, you cannot exclude or you should not exclude the possibility that you also register some gypsum precipitation. So in both cases, you must take some samples, bring to the lab, run some XRD analysis, and after the XRD analysis, you can identify the minerals and be sure if you register or you cannot register some gypsum in your horizon, in your soil. Okay, so sorry, until now, so far we cannot identify gypsum at the field very easily. Okay, and I talked with a lot of people that are expert on these gypsy soils, and even then they said, JJ, the only way to identify it's running some XRD analysis. Okay, but then why it's important to keep this RSG? Because it's expressing a very dry condition that express the precipitation of a mineral that's quite unstable. You can see here this whitish colors seems like calcium carbonate precipitations. Okay, so we cannot easily differentiate them, especially at silt or clay fractions. So the only way is just drop the acid. If you does not register some reaction, probably you are using some gypsum. If you have reaction, maybe you have both. Maybe you have calcium carbonate and gypsum. Okay. Here you have some pieces of petrogypsic horizons. Okay, so here you can see very easily the cementation, and here the cementation by gypsum. Okay. And the other option is to register also cementation or an intense precipitation of other type of materials that also has whitish colors, but in this case we have calcium carbonates. So in this case, we have a soil that cannot be classified in the previous RSG, and we have a calcic or a petrocalcic horizon in the first 1 meter below the soil surface. And this is quite important to highlight, guys. In the case of, for example, in the gypsy soils, we can find some calcic or even petrocalcic horizons too. Is not a problem, okay? But because of the gypsic or petrogypsic horizon, in this case, we must classify the soil as a gypsy soil. So if I found a soil with calcic or petrocalcic horizons and gypsic or petrogypsic horizons, so this soil should be classified as a gypsy soil. But if I only found calcic horizons or petrocalcic horizons, no gypsic or petrogypsic horizons, so in this case, this could be a calcic soil. Okay, so these calcic soils are those soils with calcic or petrocalcic below the soil surface, but in the first 1 meter, and no argec horizon above or at the upper limit of the calcic or petrocalcic horizon, unless this argic horizon also express the precipitation of secondary carbonates. Okay, something just before I open your microphone, let's just highlight, for example, the difference between calcisols and the philzins, castanosins, and chernozins. Okay, in this case, you should remember that the chernozins and castanosins, they must register calcic horizons or petrocalcic horizons, right? But in that case, we must register a chernic horizon or a molic horizon above the calcic or petrocalcic horizon in the case of chernozins or castanosins. In the case of the calcisols, no. In the case of the calcisols, we only register the calcic horizon or petrocalcic horizon. What is above, what is at the surface is not a molic horizon, is not a churnic horizon, should be any other kind of thing. Could be a numbric horizon, could be a hortic horizon, could be any other kind of thing of diagnostic horizon, but definitely is not a churnic or a molic horizon. Okay, so this is the difference between chernozins, castanosins, and calcisols. The first two, they register a diagnostic horizon that should be a churnic or a molic horizon. And these horizons, they must be above a calcic or petrocalcic horizon or horizon with protocalcic properties. But in the case of the calcic horizon, no, just calcic or petrocalcic horizons without this horizon with a huge amount of organic carbon, with high thickness, with darkish colors, with a strong grade. Okay, so let's see that someone raised that hand. No, I think that someone just. Oh, okay, no problem. Democracy, as usually. Oh, now someone. Yes, Oklo, open your microphone.
Yes. Now this having this two different classification systems, the SOL taxonomy, the WRB, with quite some differences, particularly in the area of their organic matter composition.
Yeah.
So, is there are both classification acceptable anywhere, or is it that there's a particular place you have to use WRB, or like in Brazil, for instance, which is the one which classification system do you use? Is it the soil taxonomy or the WRB?
None of them.
Yeah.
Yeah, none of them. In Brazil, we must use the Brazilian system of soil classification. That's not an international system. It's now is not. It's why I'm not teaching about it in this course, because the Brazilian system only focus on Brazil. Okay, but of course, it's not a kind of crime if you classify a soil according to soil taxonomy or WRB in Brazil. Actually, a lot of Brazilian journals, they now are asking that, for example, if you submit a paper, you classify the soil also considering WRB or soil taxonomy. Why? Because now more people can understand the soil classification that you did in Brazil. Okay, so yes, I agree with you. They have a lot of differences between them, and some similarities, but a lot of differences. And it's not like, let's say that it's not an obligation that you must use one or the other's system in each region. Of course, some countries, they does not register their own system, and then they choose one of them. For example, I know that Peru, they does not have a national system, so they use a lot soil taxonomy, especially in America, South America, and Latin America. A lot of people, a lot of countries that they does not have their own national systems, they use soil taxonomy. In opposite, in Europe, it's much more common, in Asia, in Europe and Asia, it's much more common to find WRB. So I think that depends on the region, the place that you are. It's not like an obligation that it's not mandatory. You does not need to follow that specific system, but it's much more common because people are used to that system. Why? I don't know. Maybe because they just studied more, or maybe because they did some sabbatical times in countries that people are used to that systems. For example, we have a very strong participant of Europeans in the WRB. So it's much more common to use than in Europe, in Asia, because these are places that people are improving that system. Of course, some people from Peru, from Colombia, they goes to the US to have a sabbatical, and then, or even their PhDs, and then when they return, they learn it about soil taxonomy, and because of this, they use the soil taxonomy. Okay, so yes, they are quite common. You can choose the system that you prefer, and as I said, you must choose the system according what you think that's quite important for you. Okay, for example, in my case, as I said several times, I prefer WRB. Why? Because WRB tells you much more about soil genesis. So how the soil was formed through time. Okay, soil taxonomy is pays much more attention to what can be done with that soil. So, okay, I should think about soil management, land use, some restrictions, some potentials for that. So this is the focus also of soil taxonomy. So it depends on what you plan to do with the classification. So you choose, you pick one of them. Okay. And of course you can do both. No problem. This is the best option. Okay. But of course, takes time to be used to both systems. So you decide, okay? You decide to pick one of them. But of course, when you go to one specific country, it's quite interesting to see that depending on the country, people are more used to one or another system. I know that Africa has, according to the country, have several differences too. Okay, I heard, I never was in Africa, so I heard that we have a stronger influence of WRB2, but I'm not sure. Okay, I'm not sure. And of course, I think that also depends on the country, because also some countries, they has their own system. For example, in South Africa, I know that they have their own system and works very well. It's one of the best systems in the world, and they does not use, or they does not pay too much attention to soil taxonomy or WRB. Why? Because they have one very good system. They don't need to worry about any other. Okay, so I think that depends on the country, and as I said, the aim, your aim, what you plan to do with the soil classification. Okay.
Okay, thank you.
Welcome. But of course, guys, if you want to learn a little bit more about Brazilian system, we have the previous version, the fifth version of the Brazilian system. Is written in English too, so you can just check, and you will see that we have some similarities and also some differences with the soil taxonomy and WRB. Something that's interesting from the Brazilian system is that he pays a lot of attention about Brazilian soils, about tropical soils, that depending on the region that you plan to work, will fit very well. But of course, depending the place that you plan to work, will not fit very well. For example, let's think on periglacial areas. We don't have periglacial areas in Brazil, so we don't pay attention for them in the Brazilian system. In my opinion, don't say it to everybody, okay, but I don't like very much the Brazilian system. I think that it needs to improve a lot, considering when we compare the Brazilian with soil taxonomy and when we compare with WRB. But okay, no problem. As soon as we improve the soil taxonomy and we improve the WRB through the last 50 years, we will do the same with the Brazilian system. So the Brazilian system is much younger than the other two. So, okay, I understand that we have a long path to walk and to improve the Brazilian system. And I'm quite sure that each country that thinks about their own system is the same. We have the same problems because depends on a lot of people thinking on the systems and a lot of money. Okay. So let's return. So again, guys, before I just move, it's quite important that it's quite clear the difference between calcium soils and the previous, okay? First of all, the difference between calcium soils and gypsy soils. The gypsy soils, we can maybe, just maybe, we register the calcic or petrocalcic horizons, but we register the gypsic or petrogypsic horizons. And because of these two horizons, we call it as gypsy soil. If we does not register gypsy or petrogypsy horizons and calcic or petrocalcic horizons, so maybe we can call it as a calcium soil. And the difference between calcium soils and chernozens and castanozens is that the chernozens and castanozens, they must register the chernic or molic horizons above this calcic or petrocalcic horizons, okay? In the case of the calcium soils, we does not register both cases. We does not register chernic or molic horizons above this calcic or petrocalcic horizons, okay? So great, this is quite important to highlight. Here you can see some precipitations and even some cementations of voids by calcium carbonate. Now let's see some soils that express clay migration. Okay, we have the retisols. And the retisols are those soils that first, they cannot be classified in the previous RSG, and they have an argic horizon in the first 1 meter below the soil surface, and they have retic properties. What are retic properties? Retic properties are those fingers, interfingering of one horizon inside the other one. Okay, so we have some E horizons, some pieces of the E horizons inside the B horizon, inside this argic horizon. So we have here the BTX, the BTG. So both are argic horizons because they have some shiny surfaces, or they register a high clay content and a higher clay content than above. But we have retic properties. We have pieces of this E horizon within, inside this argic horizon, like here, here, and here. So this pieces of E horizon inside the B horizon, or the opposite, it's also true. We have pieces of the B horizon inside an E horizon. So in both cases, we have retic properties, and the presence of retic properties calls the retisols. We must classify the soil as retisol. Okay, these retisols, they are more commonly related to soils that grows on forests, and these forests will have very long and deep roots that when this tree dies, the roots are destroyed, are degraded by organisms, and the space that before was filled out by the roots now are filled out by the mineral soil. So because of think like the roots that in the past could grow here and here. After this tree died, so the roots start to decompose, and then the space that was filled out by the roots then start to be filled out by the mineral material. So the space that was formed and filled out at here in the past start to be filled out by the E horizon that by gravity start to migrate from here to here, and then totally fill out the space that in the past was filled out by roots, was occupied by the roots. Okay, so it's something that you must think that when a root start to degrade, to be decomposed, some material starts to migrate from the E horizon and fill out this space inside the B horizon. Okay, so this is quite common in forests in areas that have a lot of trees with long and deep roots, and when these roots die, they induce the migration of material from a E horizon to B horizon. Okay, we have also the acrosols. And the acrosols, they have an Argec horizon without retic properties. And the Argec horizon should be in the first 1 meter below the soil surface. And we must register a CEC lower than 24 centimole charge per kilogram of clay. So we must register, in this case, low activity clays in some subhorizon of the Argec horizon in the first 100 centimeter below the soil surface. So we must register an Argec horizon and low activity clays, especially kaolinite, iron oxides, aluminum oxides. Okay, and the exchangeable aluminum is higher than the exchangeable bases in half or more of the depth range between 50 and 100 centimeters below the soil surface. So between 50 and 100 centimeters, I must register more aluminum than exchangeable bases, calcium, magnesium, potassium, and sodium, or the lower half of the mineral soil above a limiting layer starting equal or less than 100 centimeter from the mineral soil surface, whichever is shallower. So I must register in lower half of this material higher content of exchangeable aluminum than exchangeable bases. So in this section between 50 and 100, or in one of this part of dominance between 0 and 100 centimeters. Okay, but at least half of this. Okay, so the acrosols are those soils with an Argec horizon, low activity clays, and a higher content of exchangeable aluminum when I compare with exchangeable bases. So low activity clays, low content of base saturations, or low content of bases, and Argec horizon. Okay? Now, when I consider the leach soils, are those soils with an Argec horizon starting in the first 1 meter below the soil surface, and a CEC that should be lower than or should be below 24 centimole charge per kilogram of clay in some subhorizon of the Argec horizon within 150 centimeters below the soil surface. So in this case, the leach soils, we have an Argec horizon and low activity clays, a dominance of low activity clays. But in this case, the content of base saturations should be equal, exchangeable bases should be equal or higher than exchangeable aluminum. Okay, so the difference between acrysols and nitrosols is that in the case of acrysols, the content of exchangeable aluminum should be higher than exchangeable bases. Now, the lichosols, the content of exchangeable bases should be equal or higher than exchangeable aluminum. Okay? But the rest, it's equal. They are dominated by caulinite, iron oxides, aluminum oxides. Now let's see the alisols. The alisols also register an arctic horizon in the first 1 meter below the soil surface, and they register a higher content of exchangeable aluminum than exchangeable bases in the same depths that we consider for acrysols. Okay, so you can see that here we are not talking about content or CEC per kilogram of clay. So in the case of alisols, we have a high activity clays dominance. So we have here, we can register here some 2-to-1 minerals, no problem. But what is quite important that we register a higher content of exchangeable aluminum than exchangeable bases. Okay, so arctic horizons, a high activity clays, and a higher content of exchangeable aluminum than exchangeable bases. And then we see the last option between these four horizons, these four soil profiles with arctic horizons. Okay, we have other soils with arctic horizons. So in this case, these alluvisols, they register high activity clays and a higher content of bases when we compare with exchangeable aluminum. So let's see from the beginning, radisols, arctic horizon and rhetic properties. Acrysols, low arctic horizon, low activity clays, and higher content of exchangeable aluminum than exchangeable bases. Lichosols, arctic horizons, low activity clays, and higher content of exchangeable bases than exchangeable aluminum. Alisols, arctic horizons, higher content of exchangeable aluminum than exchangeable bases, and high activity clays. And the last one, alluvisols, arctic horizon, high activity clays, and a higher content of bases when I compare with exchangeable aluminum. Okay, so we can see these differences between them. The retisols is quite easy. It does not register any chemical or physical property than rhetic properties. The others will have some differences between them. Starting for those soils with low activity, clays and low content of base saturations, and then we change one of these characteristics, and then we change one of these characteristics, and we end with soil with arctic horizon, high base saturation, and high activity clays. Okay? So now we have the cambisols, and the cambisols are those soils that definitely cannot be classified in the previous RSG. So they are soils that does not register any strong or an intense soil genesis. So they have a cambic horizon that starts in the first 50 centimeters below the soil surface, and they have in this lower limit equal or higher than 25 centimeters from the mineral soil surface, or an anthracic, hydratic, ehagric, pelagic, pratic, or terric horizon, or a phregic, taionic, or vertic horizon starting at a depth equal or below 100 centimeters from the surface, okay, a titanic horizon with a texture class of sandy, loam, or finer, starting at a distance or a depth equal or below 50 centimeters from the soil surface, one, or one or more layers with endic or vitric properties with a combined thickness equal or higher than 50 centimeters in the first 100 centimeters of the soil surface. So, wow, we have a lot of options you can see here, right? So, the basically thing that you can consider here for the cambsoils, that the cambsoils are those soils that they does not fit the previous RSG. So they have some properties, as you can see here. They have some diagnostic horizons, as you can see here. But these diagnostic horizons, they are at depths or thickest that does not fit the previous RSG. So they cannot be classified as vertisols, but they have vertical horizons. But the vertical horizons, they are in this case at a depth that's much higher than the depth that I must consider for vertisols. Just as an example, or I have some influence of humans, but this influence of humans does not is strong enough or at a specific depth or specific content of artifacts that could classify the soil as a technosol or as an androsol. Okay, or I can register something with some properties and just a cambic horizon. So basically are those soils that they does not express a strong soil formation. They does not express a strong pedogenesis, just a weak obliteration of material and then a cambic horizon that express some color, some structure, but definitely is not something that has specific properties. Okay, so these are the cambsoils, quite similar to the inceptisols in soil taxonomy. Those soils that does not have a preference during the soil classification. I just should consider them in the land in the end of as one of the last options during the soil classification. And also have some soils that does not register a strong evolution, even less than the cambsoils. Let's start with the fluvisols. The fluvisols are those soils that cannot be classified in the previous RSGs and have fluvic material. And the fluvic material you can easily see here are those layers with very different colors, textures, and they has this dominant horizontal boundaries with these differences of material that came or could be connected to fluvial deposits. So alluvial deposits, materials that were added by colluvial or alluvial transports and process that bring material, and because of this we have a huge change of organic carbon content, clay content between each of these layers. But these differences, they are not expressing any soil formation process. It's just addition of material by alluvial or colluvial process. Okay, so these fluvic materials, they should have a minimum thickness of 25 centimeters, and they should start at least at 25 centimeters of depth, or even less than this, or from the lower limit of a plume layer, they should register a thickness of equal or higher than 40 centimeters, and they must be in the first 50 centimeters from the mineral soil surface. So if we have some human action producing a plume layer, so we should register a thicker layer with fluvic material, and the depth in this case should be a little lower, then this should be a little deeper, like 50 centimeters. Okay, but in both cases, fluvisols, materials, soils with a strong evidence of fluvic material, strong evidence of addition of material by rivers. Other option of soil with a weak soil formation, they are the arenasols. The arenasols are soils that cannot be classified in the previous RSG, and they register in the first 1 meter below the soil surface, with an average texture class of loam sand or sand. So they register a sandy texture, a dominance of sandy texture. So all these horizons or layers, they should register a dominance of sandy texture, okay? And layers of finer texture, if present, with a combiner thickness of less than 15 centimeters. So if eventually I can see some layers with, oh, this register like a loamy or a clay texture, the thickness of then combined should be less than 15 centimeters. And layers with 40% or more of coarse fragments, if present, they also should register a combined thickness of less than 15 centimeters. So if I register eventually some pieces of rock, gravels, these layers, they should have less than 15 centimeters combined, okay? So we are basically talking about a soil that express sandy textures, probably very, very low CEC, a high water conductivity because of the dominance of sand in this soil. Finer layers or coarse layers with coarse fragments like gravels, they should be quite thin. And the last option in WRB are the regosols. And the regosols here, we does not have any criteria. The criteria is that we could not classify these soils in the previous RSG. So we could not classify in the 31 previous RSG. So then we call this soil as a regosol. It's our last option. Okay, so regosols are those soils that cannot be classified or does not fill out the criteria from the previous RSG. Okay, so basically it's a soil that we does not fill out the previous criteria. For example, I'm showing you here a soil with the rock. It's quite close to the surface, but it's not too close to be a leptosol. We have a horizon that it's dark, but it's not too dark to be a umbric or a molic or a churnic horizon. We does not register stagnant properties. We does not have concentration of salts, calcium carbonate, silica, iron. We does not register any kind of huge amount of organic carbon. We does not have permafrost. So basically, all the properties that we can think related to the previous RSG are not present here, or if they are present, they does not fit the criteria for the previous RSG. Okay, so our last option, a soil without a diagnostic, subsurface diagnostic horizon, or at least a subsurface diagnostic horizon that does not fit the criteria for the previous RSG. Okay, they are of course quite common, okay, because they are typical soils formed in steepy slopes or dry conditions that the weathering is not intense, or the erosion, the removal of material, especially fine particles, is quite intense. And because of this, we does not register any specific soil formation process. It's just chemical weathering, but an incipient chemical weathering. Not too incipient to form a leptosol, but incipient enough to not create, for example, a cambisol or any other kind of RSG. Okay? So, guys, with this, we finish our RSG. Okay. Does anyone has any question related to the RSG, the reference soil groups? Everything okay? Okay, okay. So for now, what I'm planning to do, I will share with you a list of exercises, a list of some soil profiles, and I will ask you to classify the surface diagnostic horizon, the subsurface diagnostic horizon, and also classify according to the RSG. Okay, according to the reference soil group. This will be our last exercise before our exam. Okay, our exam I will schedule yet. Probably in the end of November, I will share with you all some soil profiles, and I will give you some time to classify the soils, like some hours, probably 3 or 4 hours, and you have this time to classify these soils according to soil taxonomy and according to WRB. Of course, for doing this kind of exam, you could consult, you can consult, you need, actually, you must check the books, the soil taxonomy and WRB. So don't worry, it's something that I need to know if you know how to consult and how to find the right order or the right reference soil group. So you don't need to memorize everything. You must check, because it's what we do at the field. We check each of the reference soil groups, each of the orders. I just need to be sure that you can find the right answer. Okay, of course, using the time. I didn't define the number of questions yet. Probably I will share like 3 or 4 soil profiles. I don't plan to share a lot because I know that takes time. For example, if you must classify 4 soil profiles according to 2 systems, takes time. Soil taxonomy, it's quite fast, but according to WRB, could take a long time. But anyway, you will have time enough to do this kind of exercise, and you just need to email me with your answers, okay? But I will define the specific date, as I said, probably the end of November. I'm checking here, probably between 14th and 15th, probably Monday or Tuesday, I will share this exercise and give you 4 hours to doing that. But don't worry, I will let you know around Thursday or Friday the specific dates, and then you have time enough to be sure that you'll be okay to do that, and you have time enough to run this exam, okay? About our field trip, for those that said that they are available to attend the field trip, I talked with the chief of the department, the chair, and the chair said that it's okay to use my own car. The university can pay for everything in this case, especially insurance. So we just need to schedule a specific time. I think that will be much more interesting to schedule this after your exam, because then you can save some time to study, and especially do the list of exercises that I will share, so we can talk by mail just with the people that plans to attend this field trip, and then we can go, okay? Any other question, guy? I know that I need to share this last slides. I will do this after the end of this class, okay? I think that are the last slides that I need to share. Any other question?
Professor, in December 2, I have exam.
December
2.
December 2? Okay, okay, Demarcus. Okay, don't worry. I will schedule this exam before December 2. Definitely, I think that will be the next week, because I need some time to be sure that everything's correct. And I also need, I must use some of this time to launch the grades on the system. So I really need time for doing that. Okay, so don't worry, it will be before December 2.
Okay. Yeah, today my internet was not stable. Please share the
Don't
document.
worry. Don't worry, don't worry. I will share the slides and I will share the video. Okay. As soon as I receive the link for the video, I will upload it on YouTube and you can watch. Don't worry.
Okay, okay. Have a nice day.
Oh, you too. So, any other question? No? Okay, guys. Thank you very much for your time, and I hope you have a great week. See you. Bye bye.
Bye bye. Thank you so much for your time. Have a
Ciao.
great
Bye bye.
Thank you. Ciao, ciao.
All right.